I'm gonna hide that. No, because I don't monetize my videos.
Why not?
Because I'm an employee of the Board of Education, and if I say you must watch this video and then I put advertisement on it, it's what's called conflict of interest, and that would be wrong. So I can't do that. I would get in trouble. Now, I'm recording this, so I would like to talk about science right now. Maybe later on we'll talk about it. Okay, just put the title, don't worry about the picture. We will explain that type of stuff in a moment. Again, it's always online. The PowerPoint is there. So we're going to talk about something called ions and how they're formed, and then we're going to talk about the charge that ions have. Okay? Now, in order to get a good understanding of this, we need to know our Lewis diagrams. All right? In the note, I do have a Bohr diagram, but the Lewis diagrams are the important thing because they're the easy way to draw it. So I just want to talk a little bit or remind ourselves about Lewis diagrams. So remember, if I have something in group 1, like sodium, how many dots do I put around a sodium atom? How many dots, Jake? Because it's in group 1, and it has 1 outer electron, all right? So we put 1 dot there, all right? I'm actually talking to a handful of people who didn't do this very well on the test. That's because maybe they missed that lesson and didn't go and watch my video, right? So that's why I'm kind of doing this, because we need to make sure we know how to do it. So if I've got something like magnesium in group 2, how many dots do I put around magnesium? 2 dots. It's in group 2. And now I jump all the way across the transition metals. If I'm talking about something like aluminum in group 3, how many dots am I putting around this? We need 3. We don't want any silly answers because we got people that don't know this. So we're going to stick with the good answers. 3. 1, 2, 3. And as I work my way across, if I'm oops, that's a bad dot there. 3. If I'm talking about carbon, how many dots, Mitchell? If I'm talking about carbon, this had 1 and 2 and 3. How many dots will carbon have? 4. Nice. 1, 2, 3, 4. Nitrogen, I think we're getting the idea. Nitrogen's going to have 5, and I like to think of it like this. 1, 2, 3, 4. Now I've got to pair it up 5. Oxygen is in group 16. It's going to have 6. 1, 2, 3, 4. Pair up 5, pair up 6. Fluorine's going to have 7. 1, 2, 3, 4, 5, 6, 7. Notice how I cheated on that one. I did 2, 2, and 2 because I've done it so many times. I know the way it's going to work. And if we get over to neon, it's going to have 8. And what do we say about this shell if it has 8? How do we describe that shell if there are 8 electrons in it? How are we describing the shell? Yeah, Nolan? You're correct. It's full. It's full. The only trick one to that is helium, and helium has how many? It has 2. Even though it's out here, it has 2, and that's because the first orbit only has 2 in it. Okay, but we don't have to worry about these guys out here because they don't react and they don't form ions. So we're not going to have to worry about them in this lesson because in this lesson, we're going to be talking about the formation of ions. Okay, that's good. We need to know that in order to do that. So, formation of ions. You can write this down. You're just adding notes. And you're doing this in Google. Turn it into a thing. Nice. It's cool. It's good. I'm just curious because, like on the iPad before, you were you know, you were writing on it, right? But that works fine too. It's awesome. Noble gases are non-reactive because their outer orbits are full. Nolan just said that. That's perfect. They don't need to gain or lose electrons. Now, normally when I teach this subject to my grade 11 university and my grade 12 university, I talk a little bit about this. And you know what? Because I teach that stuff, I can't help but bringing this up for you guys as well. We often say and help you guys remember chemistry by saying that things are unreactive because their outer orbits are full and therefore the atoms are happy. Have you ever heard a teacher say that before? Okay, so this atom here, neon, is happy. It's got 8 electrons around it and that's full and that makes atoms happy. And so then we say down here, other elements are reactive because their outer orbits aren't full. It's like we say, they're sad. They don't have a full outer shell. So they're going to have to gain some electrons, or they might get rid of some electrons to make them happy, right? Now, who's kidding who? Atoms don't have little brains, and atoms don't have emotions. They don't have feelings. But we do often use this idea to help students remember things. In reality, there's laws of physics that for some reason make 8 electrons in the outer orbit a good thing. The physics is very complicated. The physics is even a new invented physics that was created in about 1930 called quantum mechanics. In university, I took multiple courses on quantum mechanics. This is my last class's quantum mechanics textbook. And in there are equations upon equations upon equations that I used to know the math 20-some years ago. Now I have no idea what the math is. But the math is what determines that 8 electrons is good. All right? There's lots of physics behind it. No way for you to know this physics. I don't remember this physics. I just remember bits and pieces of it. We teach the grade 12 university a little tiny bit of this, a very small tiny bit that introduces it to them and gets them ready if they go on to university and learn about atoms in depth. You guys don't need to know that. What's that? No, technically it isn't rocket science. It's quantum physics, but it's not quantum science. It's not rocket science. All you need to know is the atoms have a desire, and again, I'm kind of expressing that like it's a feeling, but they don't. They have a desire to have a full outer shell or to empty their outer shell, okay? That makes them stable. All right. Click. So what is an ion? Because that's what today's lesson is about. It's about ions. An ion is essentially a charged atom. An atom that has a charge that is formed by gaining or losing electrons. Remember a few lessons back when we were talking about the atoms and how the number of electrons equals the number of protons. We had that chart that was like super easy because every number in the chart was the same, right? Remember that super easy chart? That's for atoms. During a chemical reaction, an atom will either give away its outer electrons or accept more electrons to get a full outer shell. If electrons are added or removed from an atom, it becomes charged. It becomes a charged object. It's very much like in grade 9 when you learnt about electrostatics. Remember when you learnt about electrostatics, you might have used a pith ball, right? Remember this type of thing, right? And if I take something like an ebonite rod and I add electrons to it, I don't know if it'll work today because it's pretty humid today, but if I add electrons to it, I can give that a charge, right? What charge did it become if I added electrons to it? Yep, negative. This is a large piece of styrofoam, but even if I talk about a single atom, if I add electrons to it, it will become negative, all right? I can remove electrons from this as well. I can't remove it using this negative rod. I'd have to use a positive rod to suck the electrons off of it. But if I remove electrons from something, it becomes positive. And that's true for atoms as well. Yep.
But can't you remove it by touching it? Because that removes the charge in them.
That's true. That would be neutralizing it.
Oh.
I could remove it by doing something called induction. You would have learned about it. It goes like this, but I don't know if you remember it. You'd take a negative charge, you'd bring it close, then you would touch the object, which would then push those electrons off, and then there would be positive. That's a tricky thing to do, but you can do it. Essentially, adding electrons makes it become negative, and removing electrons makes it become positive. So let's talk about that right now for a moment. So let's talk about positive ions, and they're the trickiest ones to remember. It's really easy for us to think about adding electrons to something to make it negative, but it's kind of tricky for students to think about taking electrons away to make it positive. But I think I've got a way in order for you to remember that. So positive ions have a positive charge. They're actually called cations. I don't know if we use that term in this course. Actually, I'm going to add it to it because I think it's important. So somewhere under positive ion, put cation, all right? A cation. They have a positive charge. They're formed by removing electrons from the outer shell until it's empty. So you take all the electrons away. These guys on the left, they only have 1 electron and 2 electrons and 3 electrons. They tend to lose their electrons. You might have had a teacher explain to you why they lose their electrons. I don't know, maybe you had them do this last year. Some teachers, when they talk to the grade 9s and 10s, they'll say, well, it's a lot easier to get rid of 1 than to gain 7, so it might as well get rid of 1, right? To get that full outer shell in order to get rid of it. Now again, that implies that the atoms have feelings and ideas. It also implies that the atoms are lazy. Like, think about that. Think about, what a potassium would think. Oh man, I got 1 electron. I wish I had a full outer shell. What can I do? I could get rid of the 1 that I have, or I could go find 7 more. 7, that's so many to go and find. I might as well just get rid of the 1, right? You see what I mean? It almost makes it sound like the atoms are lazy. They're really not. Again, it's the laws of physics that governs the fact that it gets rid of them. But you can think of it like that. It's okay. It might help you remember it. But in reality, it doesn't have to do with the fact that the metals are lazy and they don't want to gather up a whole bunch of electrons. It has to do with physics. But the metals, these guys in group 1, 2, and 3, they tend to get rid of their electrons. Okay? So these are the guys on the left. Let's talk about how that works. And I do want you to well, you know what? Don't draw this. Let's talk about it, okay? Let's talk about it, and then I'm going to draw the Lewis diagram for this, okay? So here we've got a sodium atom, and this is a simpler representation than our regular Bohr diagram. Notice we don't have complete circles, and notice we don't have dots. But I do have numbers here to tell us how many electrons are in the orbit. Remember, sodium is in the 3rd row. So it's going to have 1, 2, 3 orbits. So you can see there 1, 2, 3. We know that in the first orbit there can be 2. You can see it right there. And in the second orbit there can be 8. And so you can see it here. And in the last orbit there's 1. So there's 11 positive charges and 11 negative charges. When sodium gets rid of its electron, the last one is gone. Now there are 11 positive charges and only 10 negative charges. If there's 11 positives and only 10 negatives to cancel out 10 of the positives, what's the charge going to be on that ion? Yep. +1. Excellent. Says it right there. So what I'd like you to do right now is write down this and write down this, and I'm going to draw the Lewis diagram for it. It's a lot easier, okay, instead of drawing all those protons in there. So write down the two boxes, and then underneath there, I'm going to put an Na with a single dot, 1 electron. We'll fill in. I don't like the open dot. There it is. There's the 1 electron it needs to lose. I'm going to put an arrow here to represent that we're going to change something. I'm going to put in a different color an arrow here, representing that we're going to take that electron away. So we've taken it away. I'm going to put now Na here, and now no dots, because we've taken it away. So there's no dots. As you can see from the picture above, it's going to become a +1 charge. How do we represent that? We put a square bracket around it, like this, okay? And I put a +1 on the outside, okay? Now, students always have difficulty thinking about how if something loses something, like an electron, that it becomes positive. Some students always get it backwards because they think if you lose something, you should go down in some way, right? Like money. Like if you pay something out, you'd have less money. You're giving your money away. But in this case, you're giving away something that's negative. So that changes what the charge it becomes. It makes it become an opposite or a positive charge. The way I've tried to come up with an analogy or a funny story to help students think of it, I call this the hippie representation of ions. So if you think of hippies, right, if you've ever encountered a hippie, hey man, how's it going today, man? I'm feeling pretty darn good about life, man. It's a beautiful day, right? So let's say then that someone bums that guy out. Hey man, why do you got to be that way? You know, it's like you're taking away all of my
positive vibe.
Exactly. So, you know, if you actually, I've got the story backwards. Let's change it. So let's say that you're a hippie and you wanna feel better. You want to feel positive. So what do? You're gonna push away all your negative feelings, man. Just push those negative feelings away. Just push them out there into the universe, man. Because if you get rid of your negative feelings, how are you gonna feel? Logan, how are you going to feel if you push away your negative feelings? You're going to feel positive. You're going to feel good about yourself. All right? So that's my hippie theory of thinking of the charge on an ion. Right? It's pushing away its negative charge. So in the end, it's going to be positive. All right? And yes, I've put that on the internet. You can have your parents watch that. Oh, sorry about that. I do want you to write this underneath. Here, I'm going to back it up. And I'll write it underneath on the smartboard. So this is what we call a sodium atom, and this is what we call a sodium ion, all right? A sodium ion. The name doesn't change. When we have a positive ion, the name doesn't change. We're going to talk about negative ions in a minute, and you've probably heard that you can have something like, instead of oxygen, you can have oxide, right? Have you heard that before with the IDE on the end? That's for negative ions. But for positive ions, the name stays the same. So this was a sodium atom, all right? And when we took its electron away, it became a sodium ion. So we just changed atom to ion. It's that simple. So those of you who are writing ahead, you're going to notice that we already drew this. This is the Lewis diagram. We just did this. Instead of a dot, I have an X here. Here we're giving away that X. We're pushing away that negative feeling, man. What happens? It becomes a +1 charge. Okay? So now at this point, we're going to draw a bunch of ions and we're going to determine the charges. Now on my PowerPoint slide, I have it in a chart like that. Now, you guys on Google Classroom, I have given you on today's slide here, formation of cations and anions. And so you can open that up and write on it, or you could write it just on your piece of paper. If you want to write it on your piece of paper, that's fine. You actually can write on the PowerPoint as well. So I don't care how you do this. This is the same as what I have on my slide, all right? And I'm actually going to write it on the slide because it is easier to write on the slide than it is to write on the sheet. Or if you wanted to write on your piece of paper, element, group, Lewis symbol, electron, Lewis symbol, ions, name of ion, you could make a quick little chart in your note and you could write it right in your notes. So you've got many options, and I don't care how you do that. Okay? If you're using your phone, you're zooming way in, right? You know how to zoom way in and do the writing. So I'm going to look first at hydrogen, lithium, sodium, and potassium. So you'll notice, what group are all of those elements in? What's the group number? Yep, group 1. So on your chart, if you're writing it on the computer, right, you're going to have 1 and, oh my goodness, my pen is not up. Let's back up. I'm going to have 1 in that spot, and I think it goes all the way down. I'm going to put 1, 1, 1. Okay? You might get the idea of this already, and if you do, you can go ahead. What's going to be true about the amount of dots for all of these atoms? What's going to be true about the amount of dots for all these atoms? Yep. They all have 1 on the outer orbit. H, Li, and A. You can use a dot or you can use a plus or an X. I don't care. Potassium, K. You might be able to figure out how many electrons are going to be lost. Go ahead and fill that in, because you can always erase if you make a mistake. Lewis symbol. I got to have the brackets around it, and I got to have the right charge. Name of the ion. Well, we already know what it is for sodium. See if you can figure it out for the rest. And I'm going to be patient here for a moment because I want Jacqueline to catch up, and she's making a beautiful chart with a beautiful ruler. Don't sweat about it so much. You know,
all my work has to be
does it really? Okay. So we're waiting for Jacqueline. Again, don't wait for me. If you think you understand how to do it, you think you get how to do it? No? How many electrons did sodium lose?
Oh.
How many electrons, how many dots did we take away from sodium in our example? 1. So the answer to that is 1. How many electrons did we take away from sodium in our example? I just said it, but did you just Snapchat there? Is that what's happening? Don't do that. How many electrons did sodium lose? 1. How many electrons are all of these group 1 guys going to lose? 1. There's only 1 electron, so they have to lose 1. Lewis symbol, we already did sodium. Na, I need to put square brackets around it because it's a different thing. See how it's lost its electron? As soon as it becomes an ion, I have to put square brackets around it. That's just the notation. And what charge did sodium become, man, when it got rid of its one negative feeling, man? Yep, +1. It pushed away one negative. Okay, did you get the idea? Do you want me to keep doing that hippie sound? That's really annoying, isn't it? It's annoying. +1. What's going to be true about all of these ions? They're all going to be +1. They're not going to have any dots around them because we gave that electron away. You're going to have square brackets around them because that's just the way we write them. So when we did sodium, right, what did we call, when we started with a sodium atom, what did we call the ion? Correct. So for positive ions, their name stays the same as the element. You just write ion on the back end. It's that simple. And that's just the way we do positive ions. You might think, well, that's dumb. It's not much of a change. But that's just the way we do positive ions, the way it is. So, yeah, we already have here a sodium ion. So what's this top one going to be? Yep, a hydrogen ion. By the way, that dot's a dot on an I. It's not an electron. What's this one going to be? What's the lithium atom going to become? I'm hoping this is very repetitious. Quinn? A lithium ion. We've already seen the sodium ion. What's the last one going to be called? Kate? Yeah. Elements in group 1 all become the same charge. They all become +1. Now we're going to do some with group 2, and we're going to have another grid. And Jacqueline's going to be drawing more grids. The ruler's going to be flying. You know what you can, oh, you've got a great big whole page of it. You can just keep going on another page or make them smaller. I don't know. For those of you that are looking at the document, you're seeing this, all right? And I'm going to just say here, beryllium, magnesium, calcium are the group 2s, and then I've got a couple of group 3s in it. So this is the last grid when it comes to talking about positive ions. I'm saying that to Jacqueline because she's making big grids, which is okay. So those of us who are writing on a document, you're not having to make the grid. Beryllium, magnesium, calcium. Lucas, what group are we in? Group 2. Group 2, group 2, group 2. That's going to tell us how many dots to put on the Lewis diagram. So I'm hoping you can almost go ahead, right? You can now put your beryllium symbol and put your dots. How many dots? Mitchell, how many dots will these elements in group 2 get around their symbol? 2. Don't wait for me. Keep going if you think you know how to do this. How are you pulling this off? You're struggling with this because it was easier to write on it, wasn't it? So you got a double whammy. You know what can happen is if you had a device like that, okay, when you do the write on, it's going to create a new document, right? It's going to make another one, and then you can always go and look at that. You know what I mean? So you can use this one if you want, right? If you want to use this right now as we're doing this type of thing. That's the issue with the computer and with the, you know, with the things. Okay. BE 1, 2. How many electrons is this thing going to lose? 2. BE, it's going to have square brackets, but no dots because it gave 2 away. And hey, man, it had 2 negative feelings that it got rid of. So what charge will that be? +2. +2. So it gets a little +2. It's a positive ion, so its name still stays the same. So what is the name of this ion? The name of the ion. A beryllium ion. A beryllium ion. And I spell beryllium wrong every time. It's got 2 L's in it, I think, doesn't it? Berry, 2 L's, I-U-M. Beryllium ion. It's the 2 L's that mess me up. I'm hoping that you're completing the rest of the grid, not waiting for me. Boron and aluminum. What group? Logan? 13, but I'm going to just write 3. We're going to ignore the 1 because we're not going to learn about these 10. So I'm going to call this group 3, and I'm going to call this group 4, and group 5, and group 6, etc., etc. How many dots is it going to get, Logan? 3 dots. You're seeing the trend, aren't you? You're almost annoyed to the point where I'm asking, you're going, are you kidding me? 3. Correct. How many electrons will boron lose? Nolan is also understanding, and he is also feeling some impatience. Come on, man, we get the idea. That's what I'm hearing from that. Nolan, what's the charge on that ion going to be? I tell you, it's good stuff. What's the name going to be? Yeah, it's going to be a boron ion. Boron ion, and that's just fun to say because of all the ons at the end. Boron ion. All right, again, I'm hoping that you're working ahead. I'm going to just finish this off. Magnesium, 2 Mg plus 2 magnesium ion, Ca, 2 dots, 2 Ca plus 2 calcium ion, and Al, 1, 2, 3, 3, Al plus 3, oops, aluminum ion. I have to say it that way or I spell it wrong. It's terrible. So if we have ions and they're in group 1, their charge is +1. If they're in group 2, their charge is +2. And if we have ions and they're in group 3, their charge is +3. Okay? In a moment, we're going to look at the negative ions, and we're going to work our way backwards, because they're going to gain. But we're going to get to 4. And 4 has this special situation where some of the elements can gain and some of the elements can lose. These metals down here at the bottom tend to lose 4 electrons. What charge would there be on a tin ion if it were to lose 4 electrons? Jake? +4. Okay? +4. All right? Same with a lead. If we have a lead ion, it is a +4. Okay? These guys at the top of the stair-step line, they tend to gain because they're the non-metals. They tend to gain them. Okay, so the last thing I have here before we start talking about the negative ions, and again, if you're on the sheet, if you're working on the worksheet, these are the questions at the bottom. If you're working off of the PowerPoint because you opened the PowerPoint, that's great. Yep. Yeah, you can, but don't go too far. Don't go like all the way down to phys ed fancy water bottle filling territory. Just get it like right there at the step or something, yeah. Us science people are not quite as important as second floor and as phys ed people. There's one right there, but it's just a regular fountain. You know the fancy ones, the water bottle filling fancy fountain? We don't have any down here. We'd like one, don't we? Okay. What type of elements form positive ions? What do we call these guys over here on the left? Metals. Metals form positive ions. If the element is in group 1, what charge does the ion have? If this is an element that then loses its electron, what's the charge on the ion? Bella, what's the charge going to be? If I have an element in this group and it becomes an ion, it loses its electron, what charge does that ion become if it's one of these in this first group? It has to be positive because remember, it's getting rid of its electron. It's getting rid of that negative charge. But how many electrons is it getting rid of? So how positive does it become? Positive 1. Group 2. What charge do their ions become? Plus 2. It's going to get rid of 2, so it becomes plus 2. And yes, I put there group 13, but I'm going to call it group 3. We're going to ignore these guys in the middle. How many electrons do these guys get rid of? So what is their charge? What is their charge? Mitchell? Plus 3. All right. So that is the formation of positive ions. Let's now talk about negative ions. So I just did the summary there, Jacqueline. We summarized that all of these guys become plus 1 because they get rid of 1 electron. These guys become all plus 2 because they get rid of 2 electrons. And these guys all become plus 3 because they get rid of 3 electrons. Okay? But I would like to advance. So yeah, you could, let's keep going. Let's talk about negative ions. Sure, doesn't matter. So we're talking about ions, charged atoms. We've already talked about positive ions. We're now talking about negative ions. Good place to come back. But then you're going to have to watch the beginning of the video in order to catch the front half of this. Okay? Negative ions have a negative charge. And you know what? They have a different name as well that you don't necessarily need to know, but as a chemist, I feel I've got to write it down. Positive ions, I put down underneath that they're called cations. It has nothing to do with cats. It has to do with where they were discovered in a chemical reaction that involved a battery. And so we call one of the electrodes on a battery a cathode. So they're called cations because those ions went to the cathode. These ions are called anions. And they're called anions because those ions went to the anode of the battery. And that has to do with battery technology and stuff like that and the way it was discovered in the mid-1800s. So don't worry about it, but it is the appropriate term. You can think of it just in terms of negative ions as well. I just feel I got to tell you. Whoa, never thought of it that way. Word association. Negative ions have a negative charge. They're formed by adding electrons to the outer orbit until it's full. The nonmetals tend to, the nonmetals tend to gain electrons. So these guys on the right tend to gain electrons, and that's because they're almost full. Now again, that's the wrong impression. That's like saying, an oxygen atom is going to say, oh man, I got 6 electrons and I want 8. It's going to be a lot easier for me to get 2 than to get rid of 6. And no, it's not because atoms are lazy. It has everything to do with the physics involved. All right? Thank you. So we've just started talking about negative ions. You could try to start writing the note at this point, but I am still videotaping. It's going to be on the video. Okay? All right. Hey, let's focus, folks. So nonmetals gain electrons to form negative ions. My next slide again has that big picture of the Bohr diagrams, but we're not gonna write that down. Okay. So you can put example fluorine. Don't draw the Bohr diagrams. We're going to write down what's in the boxes, and then underneath, I'm going to draw the Lewis diagram. So don't draw those big circles and all that stuff. We'll look at it, but we're not going to draw it. We are going to write what's underneath the box, and then I'm going to draw some pictures here of fluorine using Lewis diagrams, the easier diagrams. But looking at this Bohr diagram, if we were to draw it, we would see that fluorine has an atomic number of 9. It has 2 electrons in its first orbit, and it has 7 electrons in the second orbit. In order to become a full outer shell, it's going to gain an electron. So an electron is going to come from somewhere, and it's going to be added into that orbit. That's going to give it 2 and then 8. And now you'll notice the ion has only 9 positive charges in the nucleus, but now 10 negative charges in the orbits. That's going to make the ion negative because it's gained an electron. It's like the hippie buddy's friend. Hey man, I got some bad feelings here, man, so I'm going to get rid of some of my negative feelings, and I'm just going to push them. I'm going to push them onto you. So then his buddy's like, hey man, why do you got to push your negative feelings on me? Because now I'm taking in your negative feelings and I'm feeling bummed out. That really sucks, man. Now I feel negative. All right. I know it's the goofiest thing in the world, but it's the way I've kind of tried to convince students that if you accept something and it's negative, it's going to make it more negative. All right? Okay? That's my hippie theory of ions. So, fluorine is in group 7. So how many dots does it get? It gets 7 dots. 1, 2, 3, 4, 5, 6, 7. And an electron is going to be added into that. Now I'm just going to draw here like I did there. I'm going to put a little E with a negative, and I'm going to put a little squiggly line going into that spot. I want to put a squiggly line instead of a straight line because I don't want you to confuse it with like a reaction arrow or something like that. So I've got an electron going into that spot. That means after that electron comes in, how many dots will this thing have? 8. So I've got to draw in now 8 dots. Now that's different than what the atom is by 1 electron. Again, because of the notation, I'm going to put a square brackets around it. That says that this thing inside the brackets is this charge that we're going to give it. What charge is it? -1. -1. Now, this started as a fluorine atom, right? It started as a fluorine atom. For negative ions, we change the ending. It becomes "ide." So this is called a fluoride ion. We get rid of the ending part and we change it to "ide." So we have a fluoride ion. Now I got some charts again, where we're going to add some electrons to various atoms. Again, it's on that big page. If you were writing on the using the the app, if you're not writing on it, you can draw a quick chart, and it doesn't have to be as a fancy of a chart as what Jacqueline's drawing, but it can be. But if this was me, I wouldn't even draw the lines. I would just put the titles beside each other along the page, and then I would just draw the appropriate picture underneath it. Again, if you had your phone or you had whatever, you could zoom in, you could draw on it, right? Because I do have that on the thing. But if you don't, just write the headings, all right? And then we'll just draw them underneath, okay? Now, I said we were going to work our way backwards, but I lied. I'm looking at this chart, and I'm starting with carbon. So I'm starting with carbon, which means I'm going to have, well, what group is carbon in? 4 or 14. I'm going to write it as 4. Because I don't worry about the 10. Because if I write it as 4, it's going to tell me how many dots I'm going to put on that thing. How many dots am I going to put on that? Bella, how many dots? 4. Nice. Oh, somebody slightly bumped my cart when they came in the door, but that's okay. You'll notice my dots aren't in a good spot because it's been moved a little bit, but that's okay. In order to get the full shell, how many electrons does carbon have to gain? It has to gain 4. It has to gain 4. Yep. It's going to gain 4. How many dots will it have around it after it has gained 4? Started with 4, gained 4, 8. If it's gaining 4 negative feelings, what charge is it going to have? It's going to have a charge of -4. Name of the ion. Carbon becomes, not carbonide, nope, carbide, carbide, carbide. It's a carbide ion. Silicon is also in group 4. Nitrogen is in group 5. Phosphorus is in group 5. I'm hoping you can continue with the trend. Don't wait for me necessarily. All right? Again, I noticed some people with different technology are struggling necessarily to get this down. It's going to be on the video, right? You can always go back and look at it, get it caught up. I'm not even going to ask anymore. I'm hoping that you guys are seeing the trend and working ahead. But if you're not sure, I'm going to just quietly fill in this chart. Okay? I might ask for help on this nitrogen one. How many dots on a nitrogen? 5. It's in group 5 or 15. How many is it going to gain to get a full shell? Bella, what do you think? If it gains 5, that'll give it 10 because it already has 5. To get a full outer, yeah, it's going to gain 3 because it's going to just need to get to 8, right? So it's going to gain 3. Apologize for that one dot, it's ugly. If it's gained 3 negative electrons, what charge does it become? It becomes -3. Make sense? I know Cade keeps belting out the answers, but I'm hoping others are also understanding when he says that. Yeah, it's okay. So notice, the number of electrons it gains determines the charge. If it gains 3, it's -3. On the previous chart, for the other ions, if it loses 3, it's +3. So the number that it gains or loses determines how big the charge is. If it gains, it's negative, and if it loses, it's positive. Oops. Oh, I screwed up. I can't fix it. See, I put an extra dot. It's no good. I wonder if I can cover it up with, oh, make it one big giant dot. Woo, that's a big electron. That's good. I like that move. One big giant dot. So again, it's going to gain 3p, 1, 2, 3, 4, 5, 6, 7, 8. Now that it's full, -3. How about some names? What's the negative silicon ion going to be called? This is fun. This was carbon, and it's carbide. This is silicide. I guess you would say silicide. Silicide ion, and I know what you're doing there. Silicide, yeah, I like it. I usually say silicide, but it doesn't make it. That helps me spell it out. How about the nitrogen? What's it going to become? Yep. Yep. Nitride. And how about phosphorus? Somebody else. How about phosphorus? Logan, what do you think? Phosphorus? Give it a shot. Got to stick an "ide" somewhere on the end. Give it a shot. Phosphide? Not bad. Yep. Not phosphoride. Nope. It's tricky. Phosphide. Phosphide ion. Okay. This last chart will bring us to the end of the table. Well, you know what? I have no problem. I have no problem. Let's just do this one. Let's just do silicon. So we'll just do this one. And we've already seen fluorine, so let's just do this one. Because they're all the same in the same group, aren't they? You're all realizing if they're in the same group, it's all looking the same thing. So let's complete just one from each other group. What group is sulfur in? 6. And what group is chlorine in? 7. So just do those. Just do those 2. Because everything else is going to be the same above and below it. Hey, guys. How many dots on a sulfur? So how many is it going to gain? So what's the charge going to be? -2. And it is sulfide ion. A sulfide ion. How many dots on my CL there, Tyson? 7. Oops. 1, 2, 3, 4, 5, 6, 7. And I screwed that up. How many does it need to gain? 1. So after it gains 1, that's going to be full. I'm going to put square brackets around it. And what's the charge going to be? -1. And what's this called? Chloride. Chloride ion. Okay? The last page here again is the summary. At the bottom of that sheet, if you're working on the sheet or if you're working off of the PowerPoint, that's fine. Oh, I'm looking at the time. Let's not worry about the noble gases because they're all full. By the way, folks, you know what I'm going to ask you to do? I'm going to ask you to finish that little statement there if you can, all right? And I'm going to tell you right now, on Google Classroom, there is an assignment. It's at the top. It's right there. It's not going to be due until tomorrow night, all right? But you can look at that already tonight. You can start looking at it. And it's very similar to what we did, right? You're going to have to, and I'm just being patient. I know my machine is running slow. You'll notice here, it's asking you to determine how many electrons are gained or lost. Then it's asking you to determine the charges, okay? And then down at the bottom, it's going to ask you to, one second as I explain this. It's going to ask you to draw some of the stuff that we did, okay? So you can start on that tonight. It's going to be due tomorrow. Yes, sir. Let me just do a stop here.